Hey you, are you tired of running out of energy? Are you tired of polluting the planet? Do you wish that you had almost unlimited energy? Well, the answer to all your problems is nuclear fusion. Nuclear fusion is a chemical reaction in which two nuclei fuse to become one heavier nucleus, along with a lot of energy. A prime example of nuclear fusion is the Sun. As you know, the Sun is massive, with a mass of 1.989 times 10 to the 30th kilograms, 75% of which is hydrogen and 25% of which is helium. The Sun has a lot of mass, which generates more gravity. More gravity results in more pressure. More pressure results in more heat. And more heat results in more movement in atoms. In other words, atoms in the Sun move really fast. Atoms in the Sun move so fast that when they collide with each other, the electrons are separated from their nuclei, forming plasma, a state of ionized matter. Now, under normal conditions, the repulsive electrostatic force will repel positively charged nuclei away from each other. But in the core of the Sun, it is possible for 4 hydrogen nuclei to crash together to form a helium nucleus. According to the law of conservation of mass, all of the mass of reactants must equal the mass of the products. But 4 hydrogen nuclei weigh slightly more than 1 helium nucleus, so where did the mass go? The difference in mass is converted into light and heat energy due to Einstein's equation E equals mc squared. On Earth, nuclear fusion reactors harness the power of nuclear fusion to generate energy. Unlike the Sun, nuclear fusion reactors don't use protium or hydrogen-1 as fuel. Instead, a combination of deuterium and tritium are used, also known as hydrogen-2 and hydrogen-3. When these two nuclei fuse, the result is a helium-4 nucleus and an extremely energetic neutron. The total energy released for this reaction is actually lower than protium and protium fusion that the Sun uses. So why isn't protium used for fuel instead? Well, the main reason is that deuterium and tritium fuse at relatively lower temperatures than protium. With less energy going into the reaction, the net energy gain increases. But where can we find these hydrogen isotopes? Well, deuterium can be easily found in seawater, which is great, seeing as that we live on Earth, which is filled with seawater. About 1 in 5,000 hydrogen atoms in seawater is deuterium. Tritium, on the other hand, is not as common. With a half-life of 12 years, tritium decays relatively quickly, and therefore is not as common in nature. Fortunately, tritium can be formed by exposing lithium to an energetic neutron. The resulting decomposition reaction produces tritium and helium. What could produce an energetic neutron? That's right! The nuclear fusion between deuterium and tritium produces an energetic neutron. In theory, deuterium and tritium would fuse inside a core lined with lithium. The reaction will release helium and a neutron. The neutron would combine with the lithium to form new tritium for fusion. The core would heat up due to absorbing the kinetic energy of the neutron. The excess heat would then go to boil water, producing steam, powering turbines, and finally, generating electricity. Nuclear fusion reactors are extremely efficient, generating 4 times as much energy as modern-day nuclear fission reactors and 4 million times more power than burning fossil fuels. And unlike fossil fuels, fusion reactors produce no greenhouse gases, with helium as its only waste. Finally, if an accident were to occur, a nuclear fusion reactor cannot melt down like a nuclear fission reactor, guaranteeing the safety of all personnel in case of a failure. With all these benefits, why aren't we using nuclear fusion reactors already? Even though fusion reactors are capable of generating huge amounts of energy, the amount of energy actually needed to start the reaction is crazy high. The temperature required in a fusion reactor is around 100 million degrees Celsius. That's even hotter than inside the core of the Sun. Containing this amount of heat is no easy task either. Any loss of heat or pressure would result in the fusion reaction stopping before a net energy gain can be achieved. Unlike nuclear fission and fossil fuels, nuclear fusion uses plasma as fuel, which is the least dense state of matter. As a result, nuclear fusion reactors must be even larger than other energy-producing sources in order to compensate for the state of matter being used. Economically, a lot of money needs to go into research, materials, and construction of a nuclear fusion reactor. Despite many of its problems, fusion reactors' upsides vastly outweigh its shortcomings. Producing large amounts of energy using something as simple as hydrogen for fuel, whilst leaving little to no waste behind, nuclear fusion reactors have the potential to replace fossil fuels as the #1 energy source for humans. Yo, that's totally amazing, right?